Welcome back to ECE 501B. One final announcement at the top are the teacher course evaluations. Those are due by 11:59 tonight. If you haven't already completed those, I would appreciate you giving me your input on that. And those will not be viewable by me before, who knows, January or February, long after the grades have been determined, so you don't have to worry about those influencing your grade in any way. But they will influence me personally and actually evaluation-wise. So please be as truthful with those as possible. Don't take them too lightly. Those do impact my future. Office hours for the time period between now and the final. I just finished one round of office hours, but I'm going to go ahead and hold some additional ones beyond what we normally have. We'll have one tomorrow, 2 hours from 11 to 1. We'll have another set on Friday morning from 9 a.m. to 11 a.m. and exams start, so I tried to schedule that to where it wouldn't completely be overlapping an exam. And Monday, maybe you won't want to be seeing me between 2 and 4. That's maybe more for the other class, but if you do have last minute questions, we can try to address those right before the final. Well, I guess it's not quite right before the final. It's 2 hours before the final. And if you do have questions and can't make those times, please email me and we can try to get those answered. Sometimes it's not real easy to answer via email, but we can try. We will have a review session on Friday in a couple of days, and that will be held in room ECE 530 from 1 p.m. to 2:30 p.m. If you have a final during that time or on the back side or front side, don't think that that keeps you from jumping in or coming in or leaving. I won't be offended if you come in partway through or if you leave halfway through, unless you throw up your hands and stomp out. Then I might be a little personally upset, but won't be too offended. But I might see you then on Friday. The final exam is Monday. It is comprehensive and it will contain all the material between the beginning of the semester and the end of today's lecture. That's the idea. And maybe even beyond today's lecture, because I have this huge list of topics I want to cover. Basically, the first 2 chapters of the new text that we were talking, or that you now have available to you, the Frank's text. That's what we'll be trying to cover today, is the idea. The process for the final, I think the last exam you had 3 sheets. I'll give you one more sheet, front and back, that you can have in your possession, but that's the only thing in addition to a calculator and something to write with that you need on your desk besides the exam. Unless you want extra paper, raise your hand if you want some additional paper to write on. But that should be consistent with what we've been doing this semester. Any questions on the final? Yes. Yes, thank you. The final exam will be held in this classroom, ECE room 107, from 6 to 8 on Monday. Hopefully it will not be locked. If it is, we'll have it out in the hallway. Bring a mat or something. There aren't too many chairs there. I bet you'll want something. Probably the floor might be a little cold, so you might want to sit on a mat. No, I hope that it's unlocked, but sometimes it's difficult at that time. Everybody's disappeared at 6 o'clock. Not us, though. Other questions about, thank you for that one. An obvious question that I failed to answer. Here are the beginning of our goals. I'm not sure how long I have to scroll to keep going through the goals, but I'm trying to lay out a map of where we're headed with this infinite dimensional spaces, or that concept, which is in Frank's. He also has some finite dimensional information in there to connect it So he sort of connects it to in chapters, well, throughout, but in specifically the material we are covering, chapters 1 and 2, there are some finite dimensional ideas and concepts to help firm up your understanding of this infinite dimensional idea, where we're dealing with signals or functions. And we talked last time about ways of classifying or partitioning signals into different sets. And we'll start there today with set partitions. We'll move into equivalence sets. We may have a lot of functions, but we may actually be able to throw a lot of those functions into one little container or partition of a set and throw the others into another piece and maybe the remaining into a third piece. And we may just divide our whole set into 3 different sets. Or maybe if it was a digital communication channel that we were needing to decode or encode, maybe we're just blocking that set into 2 different partitions. So keep that in mind when you're seeing this and say, what's going on? Just think of maybe having 2 different buckets and you're throwing some function into one bucket or another, and that allows you to form equivalencies between different signals. And 2 signals might be equivalent if they end up in the same bucket. That's one way of sort of thinking about this. Once we have these ideas of sets of signals or sets of functions instead of sets of vectors, now our elements or signals or functions, we can talk about signal spaces. We have the sets. We then might want to say, how do we determine how close these signals are to one another? What's the distance measurement? And now we may be thinking about integrating 2 different waveforms or functions to create something called a distance, or we'll define a metric. If we can now pair up a metric with functions, then we create a metric space. Then once we have this idea of a metric or separation or distance between functions, we can start talking about convergence and continuity. Once we have this idea of distance away from each other. Then we will talk about a Cauchy sequence. And this is kind of neat because now if you start going on in other material later beyond this class, you'll start seeing some of these words or phrases, and you can come back to this class and start thinking, okay, what's a Banach space? What's a Hilbert space? How does that relate to what I'm now doing? And you now know a lot based on the finite dimensional stuff that you've learned. With convergence, we can start looking at a Cauchy sequence, and this will be defined as we go today. Then we'll move into a complete metric space, which really says that every Cauchy sequence is convergent. It goes to something in that space. And once we have a complete metric space, that now allows us to move on with this idea of continuity. And once we have continuity, now we have sort of epsilon balls or epsilon disks that are surrounding each of these waveforms or functions. And if we have a countable covering, which means we can pair it up with the integers as far as these coverings of our set, then it's a separable metric space. If we can cover this up with a finite number, it stops at some point, then we have a compact metric space. These ideas, there's a lot of words or definitions, but it all starts to play together. Now that we have these coverings or these ideas of convergence and continuity, let's add what we've added before, a concept of addition and scalar multiplication with these sets of functions. So now we can add functions together. We can scale them with the scalars, and those scalars are belonging to some field where the field might be real or complex. Once we have these addition and scalar multiplications, now we can combine things. Once we're combining things, elements, which are these functions, what did we do before? We talked about, oh, if we can combine these in such a way that the only way that this combination is equal to 0, or if these scalars are all 0, then those functions or those elements or those vectors, depending on what part of the course we're after, those are now linearly independent. And we can also talk about linear subspaces. Maybe just pull a collection of those elements, and now the linear combination of those pieces produce a linear subspace in the overall set. Again, we might put this concept of length on top of that, and then we have a normed linear space. So now we're trying to take an element of our space and tie a number to it, or tie a scalar to it, and that gives us a norm, which is sort of a length. If we are given a function, how do we tie a single number to it? How do we tie a scalar to it? That's our norm. And once we have a, do you remember what a complete was? That was if we had a Cauchy sequence that was actually convergent. So every Cauchy sequence was convergent. Now if we find a sequence of functions in our normed linear space and it's complete, every one of those sequences converges and it's a member of that set, then we have a Banach space. So now we have this set of functions that have a norm associated with it, and we could have different kinds of norms, and we'll introduce some of those. Now we have a Banach space. And maybe you've heard of a Banach space. Or maybe you will, and you'll go, what in the world is that? Well, we know what it is. Or you will know what it is. Not only did we talk about norms, but we said, can we think even easier or more specifically than that? Can we now talk about angles between these? We talked about vectors, now we have functions. Can we talk about angles between these functions? And what does that mean? That's now an inner product. And we can now, if we have a space that has tied to it an inner product, and that inner product space is complete, now all these sequences that are converging are in the set or in the space, then we have a Hilbert space. So the Hilbert space is a more specific Banach space, and a Banach space is a more specific linear space. We kind of have all of these things tied together, but now that we have a Hilbert space, we now have an inner product. And what happens when we have inner products? Inner products allowed us to talk about orthogonality and signal representation so that we could use the Gram-Schmidt procedure to start taking maybe a linearly independent set and orthogonalizing that set, where we're sort of building that set up. And we'll talk about, if we get there, a time ambiguity function, or be thinking maybe if you've had any kind of random variables or random processes, autocorrelation. If we multiplied a signal with a time shifted, or if we multiplied a signal with its time shifted, let's say, sibling, and then integrated the result of that product, does it only align or give us a big number when it's right on top of each other? So how ambiguous is the time behavior of a given function? We're almost to the end of our goal, our map, which is signal representations, creating basis, and that requires that we have these ideas of lengths and norms. Then we can talk about orthogonal basis if we have this inner product. And finally, we can do an orthonormal basis by normalizing those quantities, those elements, which are functions in our space. And we can generalize the Gram-Schmidt procedure when we are talking about functions. So let's see how far we get with this list or this roadmap of material. What did we say we were starting with? Remember, we were starting with sets until we were so rudely interrupted by my computer last time, and we had to do it on the whiteboard, but we had different sets. Now that we have those sets, and we were talking about time-limited, band-limited, what else were we talking about? Pardon? Energy signals that are finite energy signals. So now we might want to know, can we use those kinds of ideas to partition a set? Or if we now have this collection, can we now divide it up into sets? So the set of sets, let's say that's now S1, S2, maybe up to capital S sub n. That's now a set of sets. That now forms a partition of, let's say, the set S, meaning S might be the entire set is S1 union S2, and we keep forming that union of those, except now, in order to be a partition, we don't want these to overlap. So we now want S1 union S2 union S sub n, but we want those to be non-overlapping. So this one, and we'll look at some examples of this. Right now, maybe it looks too general to get an idea or a feel of what's going on. But if we just drew a picture of that, maybe that's the overall set, and maybe this is now S1, maybe this is S2, maybe this is S3, S4, and S5. That's sort of a pictorial view of the entire field, or I'm sorry, the entire space S, and now we've partitioned it, and those do not overlap. That's what this intersection, being the empty set, is telling us. But the entire set is made up of the union of all of these pieces. And this partition, not this, but a partition, allows us to neatly divide, or a partition neatly divides a set. Now, to come up with a partition, sometimes it's easiest to do this by creating equivalence relations between different elements in the set. Often, the easiest way to get or obtain a partition is via an equivalence relation. And now let's define what we mean by this equivalence relation. Two elements are equivalent. And now elements, you could think about vectors with what we've had before, but now we're getting into where these are signals or functions. So two elements or two functions are equivalent if x is equivalent to y, which is what this is saying, x that's what I'm meaning by that x tilde y, if it satisfies three things. X is equivalent to itself for all elements in the set. X being equivalent to y implies that y is also equivalent to x, and that better be true for all x and y. So those two seem to be pretty obvious. And x being equivalent to y and y being equivalent to z implies that x is also equivalent to z. And that's true for all x, y, and z. And there's actually an infinite number of ways to create equivalences. So there's an infinite number of possible definitions of what makes, let's say, two things equivalent. But the rule above, or this equivalence relation, the rule just has to obey A, B, and C. So all we need for an equivalence relation is for A, B, and C to be true. And that doesn't take too much to do that. If we apply this, application of an equivalence rule creates what we could call equivalence sets, or maybe somebody you might see it referred to as equivalence classes. And we might say, okay, here is a particular set that is a collection of equivalent functions or elements. That's the set Y, such that Y is equivalent to X. And these equivalence sets allow us to form partitions in an underlying larger set of functions. We could look at it the other way too. If somebody gives us a partition, any partition is another way of defining an equivalence set. So also any partition that somebody might create defines an equivalence rule. So let's look at some examples just to maybe put this into more concrete terms. For example, e.g., 1, consider the set of integers. Meaning now S, let's say, is n such that n is equal to 0, plus or minus 1, plus or minus 2, etc. Then we can actually partition that set of integers up into two pieces, even and odd. Or we could say, oh, that's just this modulo 2 congruence. So if we do things mod 2, we have a mod 2 congruence, and that's going to then generate two equivalence sets. Where we could say, okay, the first one, let's call that S sub 1, is now all the n's such that n is equal to plus and minus 1, plus and minus 3, plus and minus 5, etc. Or that's just the set of odds. Any odd number is in that set, and those are equivalent then. If I give you 3 and I give you minus 5, you could say, oh, those two integers are equivalent in this partition. So here we have this large set, it's the integers, and now any integer belongs to one of these two sets. And whatever integer I give you, you can put it into that bucket. You can say, oh, that's going to go into the odd bucket. No, that's going to go into the even bucket. And that's then the partition of this larger set of integers, where S sub 2 is now n such that n is equal to 0, plus and minus 2, plus and minus 4, etc. And there is your even set. So that's just one illustration of these equivalence sets. What's another one? Let's consider the set of all signals except for, let's not include this more specific set, which I'm going to call the zero signal. Consider set of all signals except for the zero signal. And I'm going to call that zero signal capital S sub 0, which is now defined as some function x. So x is now a function of an independent variable t. But I'm calling signals the zero signal if x at time t sub 0 is equal to 0. Then that goes into this set, and I'm not going to even worry about it. It's going to be excluded from this partitioning that I'm going to define. Now we can partition the set of all signals except for this S sub 0. Now we can define a partition in the following way. We can create, let's say, an S plus, bless you, which is now all of our functions x such that x of t sub 0 is positive. And we could say we have an S minus that is going to be all functions x such that x at a specific time, we'll have to agree on what t naught is. Those are negative. That's our S minus. And that partition now of all functions, excluding the zero signals, that partitions all these functions, or any function that you might have. So this partition, this can be used to define an equivalence rule. where x is equivalent to y if x at t0, y at t0, that product, so those are just going to be two numbers. When we multiply them together, if they're positive, then x is equivalent to y, meaning they're either in S plus or they're in S minus. We haven't said which one, but they are in the same set, either S plus or S minus. For example, let me just, if this is all not seeming to be very clear, let me try to make it a little bit more concrete. Let's look at an example. And this is how we are now partitioning with S plus and S minus. Meaning, suppose that I now have this time interval, a to b, and I have many different functions, and I'm just going to pick 4. Let's say that I now have, maybe that's f1 of t. Now I might have an f2 of t. Maybe f2 of t looks like that. And maybe f3 of t, whoops, it's not good. Well, it could go on. We're just going to define it to be between a and b. Let's say this is now f3 of t. And maybe f4 of t is there. There's 4 functions, 4 general functions. To put them into S plus and S minus, we actually need to define a T naught, some time that we're looking at, to catalog those as a plus or a minus. And if we simply said, oh, let's just pick this point to be T naught, that's the time we're interested in. So this actually may be signals that we're transmitting through a channel, and now we receive them, we measure them, and this is what we measure. Somebody sent us something, and we measure F1. Somebody sent us something, and we measure F2. They sent us something again, and we measured F3, and they sent us something again, and we measured F4. And we would like to know, which bucket do we put these in? Or which of these are equivalent is really what we're after. But I hope it's clear from this diagram that F1 is an element of what? Which bucket? S plus or S minus? That's S plus, isn't it? It's positive when at F1 is evaluated at T naught. What about F sub 2? For that choice of T naught, it's also in the positive bucket, isn't it? Or set. What about F sub 3? Maybe I should have covered, maybe, who knows, maybe that's why it starts misbehaving, is because I continue to change colors of pins. What's F sub 3? That one's S minus. And F sub 4? Now you can guess by the color that I printed it in, right? That's S minus also. But you can see that in this particular collection of signals, F1 and F2 are equivalent. Because if we looked at that property, we would say, oh, F1 at T sub 0, F sub 2 at T sub 0, they're both positive. It's going to give us a positive number. Likewise, F1 is not equivalent to F sub 3, is it? Since if we looked at that, we would see that F1 T naught was positive, F sub 3 of T naught was negative, and now that's negative. So that's not, F1 is not equivalent to F3 just by taking these two numbers Once we've measured them, we just say, oh, what was its value at t naught? Multiply them together, and we go, oh, those were the same. They're equivalent, those waveforms, or those signals, or those elements of our signal space. And they define or partition our space. Is that clear? That's the example that maybe puts that into a little bit better or more concrete terms. Now what we have is we can actually say that the equivalence sets or what else could we call those? Equivalence classes. Those can be represented by a characteristic member. Maybe that's x hat. Meaning we could say, oh, the equivalence class for x sub hat is the set of x such that x is equivalent to x hat. And hopefully it's clear that it doesn't matter what x hat is as long as it's in that set. Question? So now the question was f1 is equivalent to f sub 2. What we were doing, the question I think was, does it have to satisfy these three conditions? And it should, by the way that we defined the equivalence relationship. We said that x was equivalent to y in this partition or in this example if x at time t naught times y of t naught was positive. That was defining our equivalence between x and y. So now if we plug that in and we interchange y and x, that will give us b. If we had x equivalent to itself, hopefully we will see that we get a positive number. If we had y equivalent to x, we didn't do a z, so we would have to do another z if we needed to show that that was an equivalence, but we just did it for pairs in this example. Where were we? Oh, so now we were basically saying it doesn't really matter which of these elements in the underlying set we pick. Because of the definition of equivalence, we can just pick one and call it the characteristic one, and now we have a set partitioned by x hat. So here it doesn't matter what element we choose for x hat. So I'll just leave it at that because they're all indistinguishable, each element in the set. So now we have signals, sets of signals, and ways of partitioning those sets of signals. Now we're ready to get into signal spaces. Just like we had vector spaces in the finite dimensional case, now we are in the infinite dimensional case, and if you go back to our lecture on Monday, one way of sort of getting there is to just have a function and then sample it at, well, look at the limit as it's being sampled at an infinite number of points. That gives you this function. So now if we start with a signal set, and we've talked and introduced different signal sets, maybe a set of energy signals, maybe a set of band limited, maybe time duration limited. If we have a signal set and now add this notion or concept of distance, then we're going to obtain a signal space. So we have a signal set plus a distance, this concept of distance, and that will give us now a signal space or a function space. And the distance, we might say, takes two elements and turns them into a real number, meaning that might represent the distance between those two elements. So this is something that maps pairs of elements from your signal space, maps pairs of elements from the signal set to the real number. Now we've boiled this distance of these two signals down into one number. That's the distance. And we can have many different definitions for distance. A distance definition D is referred to as, now we're introducing another term, as a metric if it satisfies the following three properties. A, that distance, needs to be positive. If we have two, or I should say non-negative, and the only way that distance between two elements is equal to 0 is if those two elements are identical or identical almost everywhere. So there could be points in the domain where these two waveforms differ, but overall, almost everywhere they're the same, then that's going to give us x equals to y. So the distance needs to be non-negative. The distance between x and y needs to be the same as the distance between y and x. There better be some symmetry in that distance defined. And we have the triangle inequality. If we looked at the distance between x and z, that's going to be less than or equal to the distance between x and y and the distance between y and z. And now we can introduce a metric space. If we have a set of elements plus a metric. So now a set of elements plus a metric is a metric space, meaning we can now have this set of elements S and a distance D, and that's going to give us or define a metric space. And a lot of times D might be just implied. Maybe it's the typical Euclidean distance. Now we could have different metric spaces even if we had the same set S but different metrics. If we have the same set but a different metric, then we have a different metric space. What are some example metrics? or actually metric spaces. So, and let's just stick with one set. Suppose that we have a set that is T, and T is made up of all functions defined over a domain T between A and B. So this set is all functions over a time interval, and it's actually a finite time interval from A to B. So that's our set of functions. But now, with respect to that set of functions, we could define different metrics, and each of those combinations of T with these different metrics will produce a different metric space. One way of measuring distance or creating a metric, let's say it's d sub 1, that's taking two functions in this space T. So that's some function over T between A and B. And now we may say that's this integral from A to B of the absolute value of the difference between x and y integrated between A and B. So that's distance 1. So if we looked at a point by point, T being our points, and comparing x and y, taking their absolute value, and then integrating that difference, that will give us a distance between x and y. Distance 1, or metric 1. A second metric might be to take an integral, not of x of t minus y of t absolute, but absolute square. And then take the square root. And that's our typical Euclidean distance. We look at it point by point, T, and we take the absolute value of that difference, square it, integrate that squared quantity, and then take the square root. So this is one way of trying to quantify or obtain a number that's representing the distance between two functions or two signals. And both are valid, D1 or D2. And we could even define another one. But this second one is more like what we're used to thinking in terms of a Euclidean measure. And that's what we sort of did. Now what are we doing? Because these are functions, we're not summing, we're having to integrate. That's why all these are integrals. But we could look at another distance or metric, d sub 3, which is the sup. Uh-oh, it's too close to meal time to be talking about sup, but it's spelled S-U-P, or it's supremum is really what that means. Now we're thinking pizza and have a supreme pizza maybe, but no, it's the supremum of the absolute value of the distance between x and y. Sup is the least upper bound, which means this difference, or the absolute value of this difference, visually, if you looked at it, you go, oh, it has a maximum, but it may never reach that maximum. But that's actually the least upper bound. Let's say that we were looking at this, and x minus y, we compare it, and we take the absolute value, and we see that it gets to 1.475, 1.475. Then that actually, well, maybe we could have an upper bound for that as 2, couldn't we? If it was 1. 0.475, whatever I said it was. So we could upper bound that by 3, by 10, by 20. We really want to look at the smallest upper bound of that particular quantity. That's what the sup does. And the supremum is different from a maximum because sometimes we never actually get to the limiting value. If this was some signal, let's say it was an exponential waveform, for example, maybe we never get to its maximum, so we don't want to say max, but we say there is an upper bound, and the smallest upper bound is the supremum, or the sup, and that's what we're going to call this distance. And that also gives us a number associated with how close x and y are. They may be very closely related, and then at some point in time, they may differ dramatically. And so this distance, this metric might be quite different than d sub 2. It might be quite different than d sub 1. Because now you're looking at what point in time do they have the largest separation between x and y. And here you're sort of in D1 and D2, you're looking at more of a summed average difference, sort of. One is the absolute value and the other is the square. But in this example, the whole point of this example was to say we can have different metrics. In this we have D1, D2, and D3. But now if we combine D1, D2, and D3 with T to find a metric space in 3 different cases, we now have 3 different metric spaces, even when we start with the same underlying set. So to finish up this example, that's now a metric space, TD1. TD2 is another metric space, different from TD1, and TD sub 3 is also a metric space. So these are all different metric spaces. And they're equally valid. And you may want to use one versus another depending on your particular situation. But now that we have an ability or a way of measuring distance between signals by, let's say, one of these representative metrics, now we can say, are these close? Are they converging? Is this one going to another one, going to another one? Are we getting close? Can we talk about how close things are in terms of epsilon balls or regions or spheres? Now we can get into convergence and continuity concepts in signal spaces or in function spaces. So now let's talk about convergence and continuity. We now turn to considering an infinite sequence of elements. So now you could think of a sequence of functions selected from some underlying set, let's say x, script x. So that now we might have this sequence, little x sub n, so each of these x sub n's live in this set script x. And that's, let's say, an infinite sequence of functions. with that particular set, we say the sequence, the x sub n's, is convergent if, have I used a backward E before? No. That is supposed to be saying there exists. So there exists an X, another member of that set X, such that for any positive number epsilon, for any epsilon greater than 0, another there exists a positive integer let me call that n sub 0, such that if I pick an integer bigger than n sub 0, then that means the distance between x sub n and this element in capital X set, the distance between those for whatever metric I've selected is less than epsilon. So now this infinite sequence x sub n is approaching x. I hope that's clear from this. And I can make x sub n get as close to x as I want by the choice of epsilon. This says there exists an x such that for any epsilon, if somebody says, I need you to get, with our metric, I need you to get to 0.1 away from x. Well, that means I need to, in this infinite sequence of functions, I need to get to x sub 107. And then if I go any of those others, 108, x sub 109, I'm less than whatever I said epsilon was, 0.1. But if I now say, oh, I need to get close to x in such a way that my epsilon now is 0.001, well, now my n sub 0 may have to be 2 million. So x sub 2 million is what I need to get to in that infinite sequence of functions before I get my distance from my metric for x sub 2 million to be within 0.001 of x. So it's this epsilon delta stuff. If you've had any real analysis, you've maybe seen this. If you haven't, maybe this is a little weird, but you might start just looking at it in terms of, here's a waveform, and now I have these waveforms that are approaching that x waveform. And depending on how close I want to get to x, I may have to go further into my infinite sequence of functions to get there. Yes? No. So x is some, so the question was, is x and x sub n both an infinite sequence? X is just some function, and you've now found an infinite sequence of functions that are approaching x, meaning this infinite sequence is going to be convergent to actually x if it satisfies this condition. If you can find, if for any epsilon, there is a positive integer in this infinite sequence of functions such that the distance between that x sub n and x is less than epsilon. So you're approaching x, or there exists basically an x given any infinite sequence that's convergent. So if somebody says you have a convergent sequence, they're saying, oh, there must be some x that sequence is approaching. That's more what they're saying in this particular definition of convergent. If you now have an infinite sequence in this set, and somebody says, oh, that infinite sequence is convergent, then they're saying that there's an x also in that set that those x sub n's are approaching relative to the distance or the metric that you've defined. Is that okay? So another way of expressing this is the limit as n marches off to infinity of x sub n is equal to x. Now, one thing that this requires then, if we have a convergent sequence, then this requires the elements in the infinite sequence list, in the list, to be getting closer together. If they're approaching some limit x, then x sub 100 and x sub 101 are maybe not as close to each other as x sub 1 million and x sub 1 million and 1, if they're all approaching x. So this requires the elements in the list to be getting closer together. That is, for any epsilon greater than 0, there exists an n sub 0 such that if m and n are both bigger than n sub 0, then the distance between x sub n and x sub n is less than epsilon. And if we have a sequence that satisfies this property, that sequence is called a Cauchy sequence. When x sub n and x sub n are getting closer, or for any epsilon, you can pick m and n such that x sub n and x sub n are a distance less than epsilon apart, then that sequence is called a Cauchy sequence. So that's the definition of a Cauchy sequence. A sequence with this property is called a Cauchy sequence. Now there's some relationships here. If we start with a convergent sequence, then by definition of that being convergent, it has to be associated with a Cauchy sequence. But we can't go the other way, or it's not necessary to be the other way. Somebody might have a sequence that is Cauchy. They can find an epsilon where x sub n and x sub n are arbitrarily close to each other, but there may not exist an element in the set that those are going to. So it may not imply that that's a convergent sequence. So a Cauchy does not imply that it's a convergent sequence. Now, if we can find a set of elements in which every Cauchy sequence is convergent, then we say that that set is complete. So let me write that down. When every Cauchy sequence is convergent, That means that wherever that Cauchy sequence, it's actually going to something that's in the set, that final x that it's approaching is in the set. That means the Cauchy sequence is convergent. When every Cauchy sequence in your set is convergent, we call that set a complete metric space. And that's, if you're reading along, we're only up to page 25 in the book. But they start talking about a complete metric space at that point. Let's look at a sort of a counterexample, or an example where we have actually a sequence that's Cauchy, but it's not convergent. And that's example 2.6 on that same page, 25. Let's now say that we have the collection of continuous functions, and we're going to, on some interval, capital T. We're going to call that capital C of T. So this is representing the continuous functions on some finite interval of time t. So that's now our set of waveforms, or our set of functions. We now need to define a distance. Let's just use the d sub 2, the Euclidean distance, with the Euclidean metric. That was this d sub 2 of xy being the integral from a to b of the square of the absolute value of their difference integrated from a to b, and then we take the square root. And now we're asking, is capital C of t with this Euclidean metric, is it complete? Does every Cauchy sequence converge? And I just said that I was going to give you a counter example. So the answer is actually no. So let's see what we can create or dream up to illustrate this fact or this relationship. We can find a Cauchy sequence that does not converge, or we can find a non-convergent Cauchy sequence. Meaning we need to find a sequence that's continuous, or each piece or each element in that sequence is a continuous waveform, but it's actually moving towards something that's discontinuous. So it's not converging to something in the set. The set, remember, was this set of continuous waveforms. We now need to build something up that, oh, it's continuous, but in the limit, it leaves that continuous set of functions. That's the idea. Here's the sequence. Suppose that we now define this collection of functions, we'll say x sub n of t, and that's equal to one of three expressions. It's minus 1 when t is less than minus 1 over n. It's equal to nt when the absolute value of t is less than 1 over n, and it's plus 1 for t bigger than 1 over n. Pictorially, what are we doing? So now we have some interval of time, and actually that's, maybe we just let it be from -1 to 1. Here is our interval t. And now we're saying x sub n of t, if this is, let's say this is now 1 over n and this is -1 over n, we're saying that the waveform is -1 and +1 on either side of 1 over n, and in between that, so here's 1 and here's -1. And this is now what our x sub n of t looks like. And that's a continuous waveform. And if we pick a bigger n, then this 1 over n is going to get closer to the origin. And so this is now, this transition is becoming sharper and sharper as n increases. As our infinite sequence, little n goes marching off to infinity, this is going to remain continuous, but in the limit, as n goes to infinity, what happens? Now this is going to be 1 and -1, and it's not going to be continuous at the origin. So we're approaching some non-continuous waveform. So here, what I went ahead and did, as I said, for this illustration, I let the domain of that waveform, x sub n of t, be living between -1 and 1. And d sub 2, if you actually computed this, d sub 2 of x sub n and x sub n, the distance between x sub n and x sub n is this integral from -1 to 1 of x sub m of t minus x sub n of t squared dt 1/2. And I'm just going to take the book's word for it. I haven't verified this, so don't ask me to verify it. But he claims that this is now the square root of 2 over 3n times 1 minus n over m for all m greater than n. That's the distance between. So now what we're saying, if we had x sub m, which is further in our sequence than little x, or x sub little n, then now we have 1 over m sitting here and minus 1 over m sitting there. And now we have something that's going to look like this. And we now need to take, and you can see that up to minus 1 over n and up to and beyond 1 over n, they're equal. And it's only when we're between all of this mess that we might have an interesting non-zero value in our integral. He claims that the result is going to give us a distance defined by this equation. But now what happens to this distance as n goes off to infinity? We can make it as small as we want, right? As long as we pick n big enough, we can make this distance between x sub m and x sub n any epsilon we want. So this is actually a Cauchy sequence, because we can pick an epsilon. For any epsilon, I can pick an n that will get us underneath that epsilon as far as the distance between these two waveforms or these signals. So this is Cauchy. This infinite sequence is Cauchy because there exists an n for which this square root of 2 over 3n, and we could pick m to be just one more than n if we wanted to, and that's now less than epsilon for any epsilon that we're given. But if we look at this, if we look at the sequence, which is x sub 1 of t, x sub 2 of t, etc., what does that converge to? That converges to the sine of t, which is just t over the absolute value of t. And that's not continuous, and we wanted our limit of this Cauchy sequence to belong to our original set, which was the set of continuous waveforms. But this sine of t function that is not nc of t. It's not continuous. And so we've now shown that you can have a Cauchy sequence that is not guaranteed to be a convergent sequence, meaning its limit might lie outside the underlying set that this infinite sequence of elements lives in. So it takes a little bit of a special breed of sets to be a complete set, or to have a complete metric space. Wow. I didn't get as far as I wanted, which is what I anticipated, but you can continue to look at this and get further through our roadmap. Hopefully you're not watching this. I don't want you to get sick. But we got about halfway through our list, but you can now sort of read that material to learn a little bit about what it means to be a separable, countable, or compact, linear spaces, linear combinations, normed, linear spaces that are complete. Now we know what a complete means. That's a Banach space. If we have an inner product on that space and that inner product space is complete, then we have a Hilbert space. And if somebody starts talking about Banach spaces and Hilbert spaces, you can now go, oh, I know where to find that, or I maybe know what's going to happen with that. You're starting to get to feel for what that is. So I'll definitely see you on Monday for the final, and possibly on Friday for the review session, which is located in room 530, and the review session is Friday from 1 to 2:30. Thank you for your attention during this semester, and we'll see you at the final for sure.